Welcome to The Explainer! I am so incredibly excited to have you here today. Okay, let's dive into this immediately because we have a huge amount of critical ground to cover. Welcome to the Diagnostic Clinic. This is our highly specialized forensic approach to mastering the Cambridge Computer Science 9618 syllabus. Today, we are putting a very specific, notoriously tricky topic under the microscope: solid state, or flash, memory, and its principal operations. Now I want you to picture this. The exam clock is actively ticking down. The pressure is on. We have two typical candidates sitting in that exam hall right now. Let's call them Alex and Sam. Now, Alex is our walking encyclopedia. When confronted with a complex solid-state memory question, Alex totally overloads the page with raw facts. We're talking spewing out everything about floating gate transistors, control gates, oxide layers, the whole 9 yards, but provides absolutely zero actual analysis. On the other side of the room, we have Sam. Sam rushes. Sam completely misses the specific command word requirements of the question and just gives a scattered, incomplete, surface-level answer. We are going to deeply analyze their flawed answers today, complete with the principal examiner's brutal red pen marks, and we are going to fix them. We are going to diagnose exactly why they are bleeding marks, and then, as your lead physician, I'm going to prescribe the exact procedural cure to get you to that top tier.
So the absolutely crucial question we must ask right out of the gate is this: why do students consistently lose easy marks on solid-state memory? Ask yourself that right now. Have you struggled with this? This is a topic that appears in virtually every single Cambridge examination series. The examiners literally love testing it, yet candidates across the board consistently drop the ball. Let's look at our friend Alex again. Imagine a classic past paper question that asks to evaluate the use of solid-state memory in an industrial environment. Now, Alex writes a massive wall of text explaining exactly how NAND gates work at a subatomic level. Is it factually correct? Yes, absolutely. Does it actually answer the specific prompt? Absolutely not. Alex gets 0 marks for evaluation because there is no evaluation happening. Sam, meanwhile, writes a quick sentence saying that flash memory is fast, but completely forgets to analyze the critical limitations of write cycles in an industrial setting. The stakes here are incredibly high. Missing these command word requirements and failing to provide structured, contextual analysis is the #1 reason brilliant students fall short of an A-star. We need to stop these easy marks from slipping through your fingers right now.
Here is our clinical lesson plan for today's session. Step 1, the examiner's diagnosis. Step 2, mastering core principles. Step 3, the method mark strategy. And finally, Step 4, high-scoring critical analysis. We are deliberately moving from identifying the disease, those common symptoms of failure, straight to administering the ultimate academic cure for top grades.
Let's move into Section 1, the examiner's diagnosis. We are going to look at the top exam mistakes and see exactly what killed a candidate's grade in past examination autopsies. But hey, before we continue, subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCSE, to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's get back to the diagnosis. When examiners review thousands of papers, very distinct patterns of failure emerge. We need to recognize these patterns so you don't become just another statistic in the examiner's report.
First up on the examiner's hit list, missing overflows in edge cases. In the context of solid-state memory, an edge case might be what exactly happens when a block is completely full and needs to be erased before rewriting. This involves garbage collection and write amplification. Students constantly forget to mention this. They talk about reading and writing as if it's magic, ignoring the physical limitations of the hardware. Second, ignoring boundary conditions. How does the system handle the maximum number of read and write cycles before degradation of the oxide layer occurs? Remember Sam? Sam missed this entirely. If a flash cell can only endure 100,000 write cycles, what happens at cycle 100,001? You must address that boundary. Third, writing generic answers that are not specific to the given context. If the question explicitly asks about a rugged digital camera used by a wildlife photographer and you talk about a generic climate-controlled server farm, you are throwing marks out the window. The examiner wants context. They want to see that you can apply theoretical computer science to a messy, real-world scenario.
Now here is a massive, flashing red alert straight from the examiners. Terminology confusion. Candidates consistently confuse fundamental key terminology when discussing flash memory. You might mix up pages and blocks or confuse NAND with NOR architecture. Or worse, you might use memory and storage interchangeably, which drives examiners absolutely crazy. Here is your non-negotiable rule moving forward. You must strictly define your terms before you use them in your extended responses. Do not ever assume the examiner knows what you mean, or that they will give you the benefit of the doubt. Prove it to them. To fix this instantly, we introduce the PEEL framework: point, evidence, explanation, link. You make your point about a flash memory operation. You provide evidence or a clear technical definition. You explain how it works mechanically. And finally, you link it back to the specific context of the question. That Peel framework is the foundational cure for terminology confusion.
Moving on to Section 2, Mastering Core Principles. It is time for a massive analytical mindset shift. We need to calibrate your thinking to match the exact theoretical framework and high academic standards required by Cambridge. Rote memorization is no longer enough.
Let's break down the difference in mindset. The average candidate, like our friend Alex, relies heavily on a superficial breadth of knowledge. Alex writes a paragraph saying something like, solid-state memory uses flash memory cells, it is non-volatile, it has no moving parts, and it is used in mobile phones. It's broad, sure, but it's incredibly shallow. It doesn't actually explain the why or the how. The top candidate, however, demonstrates analytical depth and connected conceptual understanding. Let's rewrite Alex's answer live, right now, using our Peel framework to see the transformation. Ready? Point. Solid-state memory provides high-speed, robust access suitable for mobile devices. Evidence. It utilizes NAND flash technology, storing electrons in isolated floating gates separated by an oxide layer. Explanation. Because it completely lacks moving mechanical parts, unlike traditional magnetic storage, data retrieval latency is significantly reduced and the risk of read-write head crashes during physical movement is eliminated. Link. Therefore, in the specific context of a mobile phone which is subject to constant physical movement and requires rapid application loading, NAND flash is the most reliable and performant storage solution. Do you see the profound difference there? That red pen mark just transformed into a glowing green check mark.
And that beautifully executed Peel paragraph perfectly illustrates the ultimate grade booster. Principal examiner reports explicitly and repeatedly state that transferring core principles to unfamiliar contexts and making cross-topic connections leads to significantly higher marks. Don't just isolate solid-state memory in a tiny compartment in your brain. How does the architecture of flash memory actually impact overall system performance? How does it relate to data representation or to operating system memory management? When Sam finally learns to link the strict hardware limitations of block erasure to the software implementation of wear leveling algorithms managed by the operating system, Sam's grade jumps from a B straight to an A star. You have to connect the dots across the 9618 syllabus.
Now for Section 3, the Method Mark Strategy. This is the secret sauce. Stop scrolling, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, this strategy is where examiners actively reward your analytical process over just the final output.
Let's rigorously walk through the standardized sequence step by step. If you follow this, you cannot fail. First, deconstruct the question. You must highlight the command word. Is it describe, explain, or evaluate? They all require vastly different approaches. Second, extract relevant data from the scenario. What are the constraints? Third, select your analytical framework, like our Peel structure. Fourth, execute with clear notation, especially if you're calculating storage capacities, write amplification factors, or transfer speeds. You must show every single step of your mathematical working. Finally, present with correct terminology. Use words like pages, blocks, memory controllers, Fowler-Nordheim tunneling, and floating gates. Don't just say, it saves data. Let's put this exact strategy to the test right now.
Welcome to the interactive workshop segment. We are going to apply this procedural framework directly to practical implementation skills. Let's start with Challenge 1, the data scan. I want you to visualize a highly complex chart plotting the read and write cycles of a flash memory cell over time against its latency. Imagine a 60-second timer counting down. Just take a brief moment and ask yourself, what is the core trend buried in that data? Think about the physics of the drive. The core trend you need to extract is that as write cycles increase, the time required to erase a block also steadily increases due to the physical degradation of the oxide layer. If you can extract that specific hardware trend and apply it to designing a wear leveling algorithm, implementing it, testing it against edge cases, and evaluating its performance impact on the system, you are demonstrating exactly what the highest level examiners want. You are showing a deep, interconnected process.
Let's dive into Section 4, High-Scoring Critical Analysis. This is where we separate the good students from the absolute top-tier scholars by focusing on evaluative thinking and mastering trade-offs.
To properly evaluate a memory management algorithm for a solid-state drive, you must break it down mathematically and logically. You must look at time complexity, how fast does it execute background garbage collection without interrupting the user. You must look at space complexity, How much over-provisioning memory is required on the drive just to manage the wear-leveling tables? And you must look at edge cases. What happens to the drive's performance when it is 99% full? This table is the exact matrix examiners use to grade you. So let's do challenge 3, speed writing. Take a quick 30 seconds in your mind to write one perfect, high-level Peel paragraph evaluating the time complexity of reading versus writing in flash memory. Think about the architecture. Your paragraph should specifically note that reading is done rapidly at the page level, which is incredibly fast, while writing requires erasing an entire block first, introducing massive asymmetric time complexity differences. That is top-tier critical analysis.
To ensure you absolutely nailed that speed writing challenge, here is a clear, actionable checklist to prove true evaluative thinking to the examiner. Did you consider multiple solutions? For instance, did you compare the use of NAND flash memory to traditional magnetic or even optical storage? Did you analyze trade-offs? Yes, flash is physically robust and lightning fast to read, but it has severely limited write cycles. That's a massive trade-off. Did you explicitly acknowledge limitations, like data retention degradation over long periods of time without power? And finally, did you justify your final decisions with hard evidence, using highly technical terms like Fowler-Nordheim tunneling or complex wear-leveling algorithms? If you can tick all 4 of these boxes in your exam response, your answer is utterly bulletproof. This brings us to a stark, defining contrast that separates the A students from the A-star students. Standard analysis merely identifies basic similarities. Writing both SSDs and HDDs store data gets you a baseline, bottom-tier mark. But comparative analysis? That requires identifying similarities and differences, utilizing very specific comparative connectives, and supporting every single claim with technical evidence. You need to use structured phrases. Listen to this. Whereas magnetic drives suffer heavily from mechanical rotational latency, solid-state drives mitigate this entirely. However, SSDs introduce significant block arrays overhead during write operations. That specific use of whereas and however, combined with technical terminology, signals directly to the examiner that you are engaging in high-level comparative thought. Okay, before we completely wrap up our master system, I want to inject a quick, highly practical memory hack straight from our diagnostic source material. Solid-state memory involves a massive amount of complex terminology and hierarchical structures. Create a mnemonic using the first letters of key concepts to help you easily retain them when you are under severe exam pressure. For example, let's look at the physical flash memory hierarchy from smallest to largest: cell, page, block, plane, die. Let's make a quick one up right now. Cats play badly playing drums. C, P, B, P, D. Cell, page, block, plane, die. Use whatever silly, memorable phrase works for your brain, but I promise you this simple memory hack will save your grade when the exam panic inevitably sets in.
Let's summarize this entire methodology into a single, powerful, overarching directive. Define terms, show clear working, justify with evidence. This right here is your computer science success blueprint. It encompasses the 3 unbreakable rules that guarantee top marks. Number 1, command word decoding. You must know exactly what the examiner is asking before you pick up your pen. Number 2, PEL framework application. Point, evidence, explanation, link. Never deviate from it. And number 3, the time management matrix, allocating your mental effort based on the specific evaluation factors we just discussed. If you systematically follow this blueprint, you will cure the symptoms of a failing answer forever.
Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they're practiced consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCS and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.